Okay, so we're going to talk about how to use the fundamental trigonometric identities. So first of all, you have a notes sheet, so we're going to use that. And I want to just go through a real quick notice and wonder kind of thing with you. So first of all, what do you notice? Well, we know that the sine of theta, when theta is 30 degrees or pi over 6, is 1/2. The sine of 45 is the square root of 2 over 2. The sine of 60 is the square root of 3 over 2. And the cosine of 30 or pi over 6 is square root of 3 over 2. Cosine of 45 or pi over 4 is square root of 2 over 2. And the cosine of 60 is 1/2. So if we take the sine of 30 and we square it, we get 1/4. If we take the cosine of 30, which is the square root of 3 over 2, and we square that, square root of 3 squared is 3, square root of, or 2 squared is 4. 1/4 plus 3/4 is 1. So sine squared of 30, or the sine of 30 squared plus the cosine of 30 squared is 1. Let's try it with the 45s. Sine of 45 is square root of 2 over 2. If we square that, we're going to get 2 over 4, or 1/2. Cosine of 45 is also square root of 2 over 2, so we square that. We're also going to get 1/2. And lo and behold, 1/2 plus 1/2 equals 1. Well, it makes sense that the sine of 60 squared plus the cosine of 60 squared is also going to get us 1. But let's try just some random number, like the sine of 137 degrees. So if I take the sine of 137 degrees, which is 0.682 roughly, and I square that, I get 0.465. And if I take the cosine of 137, which is a negative 0.731, and I square that, I get 0.535 roughly. What do these add up to? Once again, 1. So we've discovered something called a Pythagorean identity. That the sine of an angle squared plus the cosine of that same angle squared adds up to 1. Now, mathematicians are notoriously lazy. They don't like to write any more than they absolutely have to. So one of the ways that we can eliminate some writing is to eliminate the parentheses. However, if we're going to square the sine of an angle, it may look like, if we write it this way, that we're squaring the angle itself rather than the sine of that angle. So instead we write the sine squared of theta plus the cosine squared of theta equals 1. Or the sine squared of x plus the cosine squared of x equals 1. Now you may be wondering if that is unique to these particular trig functions, and the answer is no, because we can actually do this with other trig functions as well. So we know that if we divide the sine by the cosine, we get the tangent because of a quotient identity. Excuse me. And so let's do that. Let's divide each of these by the the cosine squared of theta. Which is legal as long as we're dividing every single term by the same value. And so sine squared over cosine squared is going to be tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is the secant squared. So we have a second trig identity. And if we had taken the sine squared of theta plus the cosine squared of theta equals 1 and divided it by the sine squared of theta, dividing every single term by the same thing, we get 1 plus, well, cosine squared over sine squared. Cosine over sine is the cotangent, so cosine squared over sine squared makes sense that it would be the cotangent squared. And 1 over the sine squared is the sine is the reciprocal of the cosecant. So we have 1, 2 trig Pythagorean identities. And so these are our new ones. We already know the reciprocal identities. The sine is 1 over the cosecant. Cosecant is 1 over sine. Cosine is 1 over secant. Secant is 1 over cosine. And the tangent of theta is 1 over cotangent of theta. And the cotangent of theta is 1 over tangent of theta. We also know our quotient identities, that the tangent of theta is the sine of theta divided by the cosine of theta. The cotangent of theta is the cosine of theta over the sine of theta. Our new ones are the Pythagorean identities. The sine of theta squared plus the cosine of theta squared is equal to 1. 1 plus the tangent squared of theta is equal to the secant squared of theta, and 1 plus the cotangent squared of theta equals the cosecant squared of theta. One way to remember the other two is to say, wait a minute, I realize that 1 is being added to the tangent squared and 1 is being added to the cotangent squared. Tangent, cotangent, same side. And T and S are close together in the alphabet, so 1 plus the tangent squared of theta equals the secant squared of theta. And C and C are the same letter in the alphabet, so they're close together in the alphabet, obviously. And so 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. Just one way to kind of connect them in your brain. So now when we have a problem like this, where we're saying the cosecant of u is a negative 5/3 and the cosine of u is positive, find the value of the other 5 trig functions, rather than building a triangle, a right triangle, deciding which quadrant it happens to be in, and building a right triangle, we can use a Pythagorean identity to do this. So from before, we realized that 1 plus the cotangent squared of u has to be equal to the cosecant squared of u. And so 1 plus the cotangent squared of u has to be negative 5/3 squared. So if 1 plus the cotangent squared of u is 25/9, and I want to solve for the cotangent squared of u, I can subtract 9/9 from both sides, and the cotangent squared of u will be 16/9. When we take the square root of both sides to eliminate the squaring, the cotangent of u is now either a positive or a negative 16/9. The square root of 16/9. So we ask ourselves, okay, if cosecant 1 over the sine of u is negative and the cosine is positive, which quadrant do we have to be in? Well, all students take classes, all are positive. Sine is positive, tangent is positive, cosine is positive. If the sine is negative and the cosine is positive, we have to be in quadrant 4. That makes the tangent negative. So we'll have a negative 4/3 for the cotangent, a positive negative 3/4 for the tangent. Cosecant was negative 5/3, so sine will be a negative 3/5. We find the reciprocal by flipping. And now we simply have to find the cosine of u and the secant of u. And if the opposite and the adjacent are given by tangent, and the opposite and the hypotenuse are given by sine, then the cosine has to be the adjacent over the hypotenuse, and the secant is the hypotenuse over the adjacent. So if we're asked to simplify something like sine squared of x times the secant of x minus the secant of x, what usually throws students off is they tend to dislike this chapter because it's a big jump. Remember that jump when you were in class And first, numbers were everything. Math was all about numbers and geometry and spatial relationships and so forth. And then suddenly a variable popped up and you entered pre-algebra and algebra. Well, this is somewhat like that jump because now we're moving from algebra with numbers and variables into our trig functions. And so when you see something like this, ask yourself, would I know how to do something to simplify something that was more algebraic? So if I had an x squared times a y minus a y, could I do something with that? Well, they both have a y in common, so I could factor that y out, take the greatest common factor out, and have an x squared if I divided this by y and this by y, and a minus 1. And then I would know what to do with it. I'd call it y times x plus 1 because I see a difference of squares, and y times x minus 1. The same idea applies here. We can try to simplify this by factoring. So when I notice that they both have a secant of x in common, I can factor that secant of x out. It's the greatest common factor. What remains is the sine squared of x and a 1, a negative 1. From here, we could further factor it, but hopefully, since we just saw it, you recognize that whenever we see sine squared of x with a 1, it could potentially be a Pythagorean identity. So we know that the sine squared of x plus the cosine squared of x is equal to 1. If I brought this 1 to the left side of the equation by subtracting from both sides, then I would need to move the cosine squared of x to the opposite side by subtracting it from both sides. And so now I know that this is really the secant of x times a negative cosine squared of x. And the secant of x is the reciprocal. So we factored, we found the greatest common factor. We used a Pythagorean identity. And since the secant is the reciprocal of cosine, it might be helpful to write it as 1 over the cosine of x. And now if I have 1 over the cosine of x times a negative cosine squared of x, I have a cosine in the numerator and a cosine in the denominator, so I can simplify, I can cancel factors, and I will end up with just a negative cosine of x. All right, so let's try and see if we can simplify tangent of x times the sine of x plus the cosine of x. So first of all, let's ask ourselves if we know anything at all about any of them, and we know that the tangent of x, because we know the quotient identity, that the tangent of x is the sine of x over the cosine of x. And that's being multiplied by the sine of x and added to the cosine of x. So if we have a fraction, the sine squared of x over the cosine of x, that's being added to the cosine of x, just simplified there, then anytime we're adding a fraction to a number, we always get a common denominator. So if we get a common denominator, we're going to multiply the numerator and denominator of the cosine of x by the cosine of x. Because we're multiplying by 1, that's legal, that's legit. And so now we will have a sine squared of x over a cosine of x plus a cosine squared of x all over that common denominator. And so I simplified here. But what is the sine squared of x plus the cosine squared of x? That's a Pythagorean identity. It is 1. So if I take 1 and divide it by the cosine of x, I have a reciprocal identity that says that that is the same thing as the secant of x. All right, to simplify this particular problem, we have a secant of t over a tangent of t minus a tangent of t over 1 plus the secant of t. So let's do the same thing. Let's get a common denominator. And that means that we'll be multiplying the numerator of our first term by the denominator of our second. So 1 plus the secant of t over 1 plus the secant of t. And we'll multiply the numerator and denominator of our second term by the tangent of t. So our common denominator will be a tangent of t times 1 plus the secant of t. And in the numerator of the first term, we will have a secant times a 1 plus secant. So a secant of t, if I distribute through, plus a secant squared of t. And then we'll have a minus the tangent times tangent is tangent squared of t. So now if I think back to my Pythagorean identities, I know that 1 plus tangent squared of theta is equal to secant squared of theta. So secant squared of theta minus the tangent squared of theta, if I subtract tangent squared of theta from both sides, should be equal to 1. So I have a secant of theta of t minus, or I'm sorry, plus, this is a 1 over a tangent of t times 1 plus the secant of t by using a Pythagorean identity. And in the numerator, I have a secant t plus 1. In the denominator, I have 1 plus the secant of t. They're both factors, so we can cancel factors or simplify. And in the numerator, I'm left with a 1, and in the denominator, I'm left with a tangent of t. And I know that that's not as simple as it can get because I have a reciprocal identity that says 1 over the tangent of t is the cotangent of t. Which means that had we graphed that big mess, we would have simply seen the cotangent of t. They are equivalent to each other. So we can be asked to factor trig expressions. And when we're asked to factor trig expressions, it's similar to if we were asked to factor algebraic expressions. Cosine squared of x minus 1 is like taking an x squared minus 1 and factoring it. That's a difference of squares. So we'll find the cosine of x plus 1 times the cosine of x minus 1. Sine squared u minus 3 sine u minus 10 is like an x squared minus a 3x minus a 10. We would need an x times an x, and factors of 10 that can subtract to become 3 are a negative 5 and a positive 2. So this will factor into the sine of u and the sine of u, and a negative 5 and a positive 2. However, we run into a snag when we see secant squared t minus tangent t minus 3. This is like saying y squared minus x minus 3. But we know a Pythagorean identity that says that 1 plus the tangent squared of t should be equal to the secant squared of t. And so in place of secant squared of t, we can substitute in 1 plus the tangent squared t. And then we still have our negative tangent of t and our negative 3. So let's combine our like terms. Tangent squared of t minus the tangent of t minus 2 can now be factored into tangent of t and a tangent of t and a negative 2 and a positive 1. So don't let the fact that they're trig expressions change anything. You still know how to factor algebraic expressions, so we know how to factor trig expressions. If we're asked to rewrite this so it is no longer a fraction, some students want to break it up and say, well, this looks like 1 over the secant of x and 1 over 1, but realize that we can't take 1 over 4 minus 3 and say that that's 1 over 4 minus 1 over 3. They're not equivalent. So we have to come up with a different strategy. So that strategy is to multiply by something similar to its conjugate, or what we would talk about as a conjugate if we were working with complex numbers. So the secant of x plus 1 multiplied by the secant of x minus 1 gets us a difference of squares. And if we multiply the denominator by secant of x plus 1, we have to multiply the numerator by secant of x plus 1, so we're actually multiplying by 1. So in our numerator, we would have a secant of x plus 1. In our denominator, if we distribute this out, we get a secant squared of x plus a secant of x minus a secant of x minus 1. From our Pythagorean identities, we know that 1 plus the tangent squared of x will be equal to the secant squared of x. And the secant squared of x minus 1 would be equal to the tangent squared of x. So in place of the denominator, we're going to do a Pythagorean identity and call it the secant of x plus 1 over the tangent squared of x. So it doesn't seem like we've made much progress because we still have a fraction. However, now that the sum is in the numerator, not the denominator, something like 4 plus 3 over 7 is the same thing as 4 sevenths plus 3 sevenths. So we can now split this. We have a common denominator, so we can call this the secant of x over the tangent squared of x plus 1 over the tangent squared of x. Well, hopefully that you recognize the quotient identity here. We have a 1 over the tangent squared of x, and that can be written as, apologies, not the quotient identity, the reciprocal identity. That can be written as the cotangent squared of x. We no longer have a fraction there. And so now we have a secant of x times a, let's bring that tangent squared up again, a cotangent squared of x. And we can tighten this up just a little bit because the secant of x is 1 over the cosine of x. A cotangent squared is a cotangent times a cotangent. But we have another cotangent to work with, and that is the cosine of x over the sine of x, and a cotangent squared of x. Cosines will cancel, and we'll be left with 1 over the sine, which is the cosecant of x, times a cotangent of x plus the cotangent squared of x. No more fractions. Finally, we are asked to use the substitution x equals 3 sine of u for u between 0 and pi over 2 to express 9 minus x squared as a function of u. So that simply means that everywhere we see an x in this function, we're going to substitute in 3 times the sine of u. So we will have a square root of 9 minus 3 sine of u squared, or 9 minus 9 sine squared of u. What do they have in common? It looks like they have a 9 in common. So if we factor that 9 out, we're left with 1 minus sine squared of u. And that is a Pythagorean identity. Sine squared u plus cosine squared u equals 1. And so 1 minus the sine squared of u has to be equal to the cosine squared of u. So we have 9 times the cosine squared of u, and we're asking you to take the square root of that. The square root of 9 is 3. The square root of the cosine squared is the cosine. So your assignment is to do the fundamental identities sheet that's next in your packet.